Happy pre-calculusing. Here's the do now. Once you have your answer, you can resume. But in the meantime, pause. Yeah, nice work. All right. So for number one, I was given miles. I used the green conversion factor up here so that my units of miles in red would cancel with my unit of miles in green. And that leaves me with multiplication. 3 times 5280. For number two, since I was given 180,000 feet, I used a blue conversion factor so that my units of feet in purple and my feet of in blue, one is the numerator, one's the denominator, and they will cancel each other out, and then it is a division. 180,000 divided by 5280. So interestingly, both problems use the same conversion factor, more or less. I mean, we could say it's the same. So it's the same numbers as far as the conversion, but we use the reciprocal because in one case we're going from miles to feet, and the other case we're going from feet to miles. We'll see that again later today. Today, we're going to be looking at angular speed, rotational speed, and linear speed. Our learning target is that you'll be able to convert back and forth between each of those types of speed. Really, there's like 6 pairs from angular to rotational, rotational back to angular, and so on. 6 different types of speed conversions, 6 different conversions, 3 types of speed. So let's find out, first of all, what are these things? So let's start with rotational speed. So I've laid the notes out in a particular format. So we're going to start with rotational speed. I'll talk about that right now, and then you can see angular speed is up next. So that is going to be an important detail when we get to the conversion factor. But since we're not there yet, let's just back up. So the bullet points for each of these different types of speed go in the same order. The first bullet point is going to be like a definition, which may, in some cases, may not actually be very helpful for like, what does that actually mean? But the definition. The second bullet point is going to describe the units used. And then the third bullet point gives us an example. So rotational speed. How many times an object rotates per unit of time? Okay, so rotation implies some sort of circular motion. And uh, in the study of rotations, we use different words often. So spin would be a synonym. I wrote that on here. Circles or cycles or revolutions. And so if you have a background in science, you remember learning about planets and moons and things. Rotations and revolutions are not the same in that context. In the study of what we're going to be learning here in pre-calculus, the difference between a rotation and a revolution is completely irrelevant to what we're studying. I'm not saying they're the same thing. That's not true. But they are completely interchangeable for our purposes in pre-calculus. So a lot of times you're going to see some different words, and a lot of people ask often, like, well, why did you change that from rotations to revolutions? And well, because I want my units to match as I'm going through a problem. And so if it says revolutions here or rotations there, but then the next place, it mentions a different word, or if I look at my notes and I see a different word written in my notes, I'm trying to make sense of it, I might change some words. Okay, so there are different words that can be used to describe the circular motion: rotations, revolution, spin, cycle, trip around a record player. There's lots of ways to describe this circular motion. Rotational speed is always going to be measured in revolutions per unit of time. A common example is revolutions per minute, but we can also use rotations per minute. That happens very frequently as well. An example is we think about a clock. The minute hand on a clock is going to go around one time every hour. So the rotational speed of the minute hand of a clock is going to be 1 revolution per hour. Okay, so after that comes the conversion factor. So from rotational speed, we can convert to a number of different things. So I want to make sure that we understand the conversion factor that is listed there is not always the conversion factor you're going to use. This is only if you need to convert from rotational speed, which is the first thing we talked about up here in green at the top of the notes page, and you need to go from rotational speed to angular speed, which is, you can see the title there is next, that's in blue. Okay, so the conversion factor, which you can see right now, is only if you need to convert between rotational speed up here in green, angular speed in blue. If you need to convert to a different type of speed, like say linear speed, this is not the conversion factor that does that, right? So I placed the conversion factor like literally between the two types of speed on the notes page that you would be converting between. Okay, so this conversion factor is 2 pi radians over 1 rotation. That word rotation you can substitute out. You could use 1 revolution, you could use 1 cycle. Any of those other words that mean the same idea can be placed there. And then just like we saw in the do now, sometimes conversion factors, we do reciprocals depending on which direction you are converting, right? So the 2 pi radians is the numerator and 1 rotation in the denominator. You might have to switch those depending on which direction you are converting. If you're going from the green to the blue, then you're going to use 2 pi radians over a rotation. If you have a blue angular speed and you need to convert to rotational speed, you'll need to do the reciprocal of this conversion factor so that your units will cancel correctly. All right, next up we have angular speed. Let's look at angular speed. So angular speed is the rate at which a rotating object's angle changes. And you're thinking like, I don't know that rotating things have angles. Like if I think about a tire on a car, like is there an angle on there? Well, that's kind of a weird way to think about it. And so, I mean, it doesn't, but it does really. Um, So the maybe a better way to describe this is just with the next bullet point. It's like rotational speed, except it is using different units. So instead of describing this in terms of complete rotations or complete revolutions, like we do in the rotational speed at the top, now we're going to measure how many radians the object rotates through per unit time. Okay, so angular speed is measured in radians per unit time. The time unit can change. Maybe we use seconds or minutes or hours or days or whatever. But angular speed will always, 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 always be measured in radians. This word does not ever change. So with rotational speed, sometimes we use different words. Could be rotation, could be revolution or cycle or circle or whatever, right? But with angular speed, it's always, 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 always radians. It's just radians. There's never anything else except radians. So an example, let's look at that same example we had last time. The minute hand on a clock, it's going to take 1 hour to go all the way around. Well, 1 cycle all the way around the clock, if we're measuring it in radians, it's 2 pi radians makes 1 circle. So our angular speed for the minute hand of a clock, 2 pi radians per hour. Right? So it's just describing the rotation using different units. We could do this in degrees, but that would be terrible, and we're not ever going to do that with degrees. But it'd be the same thing, right? It should be 360 degrees per hour. It's just describing, instead of complete circles, it's describing it in terms of what the angle measurement we're using. Okay, so conversion factor. If you need to convert between the blue angular speed and linear speed, which will come next in purple, the conversion factor to get between angular speed and linear speed is written onto the notes page, like literally between those two linear speeds. So if you can identify, hey, this problem tells me angular speed, I know that because it said radians, and the directions ask me to find linear speed. I know that because we don't even know what linear speed is yet, but because we can identify that, then on your notes page, find angular speed, linear speed's right next to it. You use the conversion factor that you can see right here. That is literally between them, right? So the conversion factor between angular speed and linear speed in quotation marks. So I put things in quotation marks that you're going to replace. That's like the label, but you need to actually put the length of the radius. So if you're dealing with a particular circle in this problem, and you are given the radius, or you measure the radius, or you calculate the radius, or whatever, when you get that number, right? Like this circle has a radius of 2 inches. You're going to put in your conversion factor 2 inches on the top of this conversion factor. And then the word one radius is going to stay on the bottom. So one radius will always be part of this conversion factor, but in quotation marks, you're going to replace that with an actual number measured in whatever units you measured it with, right? Whether it's inches or centimeters or miles. Okay, last one, linear speed. So linear speed is I'm sorry, that was too far, is the rate at which a point on the circumference of a rotating object is moving. The classic example here is if you think about a tire on a car or a truck, if there's a rock stuck in that tire tread, the rock you can imagine spinning around and around and around and around and around. Okay, well, how fast is that rock going in linear speed, right? We can measure like, oh, it's doing this many rotations or it's rotating through this many radians. But when you're driving, like we described that speed in linear speed, right? If your truck is going 20 miles an hour, that rock that's wedged into the tread on your tire is also going 20 miles per hour. So it's going to be measured in distance per time. We use lots of different kinds of units for distance. It could be miles, like I just mentioned. It could be centimeters or inches or whatever we measure distance with. And the unit of time can change. Could be seconds, minutes, hours, days, years. So you're not always going to see the same type of unit. Linear speed, there's a lot of different variations. It's always going to be some measurement of distance and some measurement of time. But there's not like that one thing you can always hone in on, like you could with angular speed that will always, always, always have radians as the unit. So linear speed, lots of different possibilities. And the conversion factor, let's just look at this bottom conversion factor. The conversion factor to get between linear speed, which you can see on the notes page here in purple, and rotational speed, which was back up at the top of the page in green, that conversion factor is given here. So the notes page, as I mentioned, has these conversion factors placed strategically. So if this is your page of notes and you've got linear speed down here at the bottom, imagine looping your page of notes to make a big circle. Look at it from the side. A linear speed is written on the bottom of the page down here. And if we're going to go back to rotational speed, which is at the top of the page, we need the conversion factor you can see on the screen right here. So you're going to use the word one rotation, and sometimes we use an interchangeable word like revolution, cycle, circle, spin, right? Some variation of rotation or circle. And then the other part of our conversion factor is the circumference. Yeah, I put that in quotation marks. Anything I put in quotation marks, you're going to have to replace. You do not put the word circumference. You actually calculate what is the size of the circumference for this circle. So circumference 2 times pi times the radius. You will need to put that into numerical. You leave pi, but put that into numerical form, calculate the size of the circumference, and that goes into your conversion factor as a number and a unit, whatever you measured the radius in, whether that was like centimeters or inches or whatever. Okay. Oh, it's Math Cat! I've been replaced by Math Cat! Seems actually Pepper. He's our mascot for math class. He's your math mascot. Our mascot. Our mascot! Yeah, alright. That was a bad pun. Hey, so math cats! Normally math cat is sitting right over there. But this morning, Math Cat found a ladybug on a record player. So I have two cats, Pepper, pictured here, and his brother Salt. Salt's probably going to show up in a later problem. So Mr. J's cat, Pepper, spotted a ladybug spinning on a record player. You can see it right there, larger than life. So Pepper, being a math cat, decided to count how many times the ladybug spins around, and he found out the ladybug does 16 spin cycles on the record player in 40 seconds. And we're going to do some math here. We go. Number one, What is the rotational speed? Measured in revolutions per minute. So revolution and rotation, two different words that for our purposes mean the same thing. Both of those refer to circles, cycles, spins, a trip around a circle. Okay, so let's take a look back at our notes. Rotational speed, how many times an object spins per unit time, rotates per unit time, revolves per unit time. So if I ever counted that, I know how many times that object spins per unit time. So in order to calculate the rotational speed, I'm going to take the 16 spins divided by the time, which was 40 seconds, and we'll divide. And if I want to change this word, I could totally change this word. I can use revolution instead, because the directions did ask me to use revolutions per minute, and revolutions means the same thing as spins or cycles, trips around the record player. That's way too long to write, so I'm going to stick with revolutions. Okay, so the other thing I noticed in the directions is it does ask me for revolutions per minute, and right now I got 16 revolutions every 40 seconds. I could divide, and that will give me a rotational speed, but not the one the directions asked me for. Let me erase this equal sign. Let's convert. I got seconds written down right now, but the directions ask me for minutes. I need to convert from seconds to minutes. So here's my conversion factor. I remember, I think, like 60 seconds in a minute. Obviously, just kidding. All right, so I want 60 seconds to go in the numerator so that the seconds in red, we're going to cancel those seconds in green, the numerator here, the denominator there. Losing letters. Seconds here, cancel with seconds there. Now I have set up problem correctly. I'm going to find my answer and drop it in that box right there. So I'll need to do 60 multiplied, I'm sorry, I said that in the wrong order, 16 multiplied by 60 and divided by 40. 16 times 60 and divide by 40. I can do that all at once on this calculator. Equals 24 revolutions per minute. I want to put the 24 up as part of that numerator, 24 revolutions on the top over 1 minute. I could totally do that. That's fine. I can leave just the units as a fraction, revolutions per minute. All right, what is the angular speed in radians per minute? Okay, so I remember I just found rotational speed in part one. This is my rotational speed, 24 revolutions per minute. And now I'm being asked for angular speed. This sounds like I need to convert my previous answer of rotational speed into angular speed. Let's go to the notes. So rotational speed in my notes page is in green. Right underneath that is where I found angular speed. If it wasn't labeled in the problem, I could identify them because my first answer was giving revolutions per minute, which here it's bullet point number 2. That's how I identify rotational speed, revolutions per minute, or some other unit of time. And angular speed is going to be measured in radians per time unit. So my conversion factor that is written down onto the notes page between those two headings, rotational speed and angular speed, is right here. Conversion factor between rotational and angular speeds, 2 pi radians and 1 rotation. And I can change the word rotation to be revolution or cycle or circle or spin or trip around the record player or whatever is going to fit the problem. But 2 pi radians and 1 rotation, and I may need to do the reciprocal with my conversion factor just to make sure that the units will cancel correctly. Okay, so I'm going to start with the 24 revolutions per minute, and then I'm going to get my conversion factor. So I know that I have revolutions on the top of the blue part already, so I know that I want revolutions to show up in the bottom of my conversion factor. so that it will cancel appropriately. So 2 pi radians is going to go in the numerator, just abbreviate everything to 3 letters. Blue revolutions and red revolutions are going to cancel. Problem is now set up correctly. Answer box. So the units, let's look at the units first. What's left? On the top, I have radians, and on the bottom, I have minutes. Those are the only units left, and that does match the direction that asked me for radians per minute. Nice. And then I'm just going to do mental math. 24 times 2, that's going to be 48 pi radians per minute. We're going to leave pi as part of our answer. That is customary when we're dealing with angular speed. I know if you were like to describe how fast your car was going down the street, you're probably not going to describe the tires going like 48 pi radians per minute, just as an example, because nobody would have any idea what that is. But that is how we describe angular speed. Okay, well, that's too many questions at once. Number 3. The ladybug is sitting 23 centimeters out from the center of the record. All right, math cat. He also does measurement. He's measurement cat on his off days, math cat the rest of the time. So 23 centimeters out from the center of the record. What is the ladybug's linear speed? All right, well, there's a bunch of stuff going on right here. Let's go to the picture. There's my ladybug. This is a still shot, but if we had a video, the ladybug is going to go round and round and round and round, make a red blur, right? It's going to trace out a circle. It's like a little ladybug tracer. The radius of that circle from the center of the record player out to the ladybug, that's 23 centimeters. You can't read that because too scribbly, but that's the radius. The size of the radius is 23 centimeters. All right, we want to find the linear speed, and the directions are asking us for centimeters per minute. Okay, we have 2 options for how we can get to linear speed. One option is we can use the previous answer from number 2, our angular speed, 48 pi radians per minute. We can convert that to a linear speed. Or other option is we could back up all the way to number 1. We can take this rotational speed of 24 revolutions per minute, and we can convert that to linear speed. It doesn't matter which one we choose. You're going to get the same answer either way. It's just a matter of you can use a different conversion factor and a different starting point. So you can go ahead and we'll vote. You guys want to use the rotational speed or the angular speed? Sorry, that's ridiculous. Obviously, you can't vote on a video recording. So I'm just going to go with the one that we can see because we can see it. 48 pi radians per minute. I'm going to set that up, and then let's go back to our notes and figure out what is our conversion factor. So this is angular speed from problem number 2, and I need to convert angular to linear. Okay, so our notes page, we're going to scroll down here. Okay, so the blue one is angular speed. We're trying to find linear speed. That's the purple one. Written right in between those 2 headings on the notes page is the conversion factor we want. It's the length of the radius in quotation marks. That means we replace it with an actual number and the word radius. Replace anything in quotation marks, always. Okay, so the size of the radius is a number and the word radius. I have to change colors here. We'll use green this time. That's actually not green. All right, computer. We're going to use green this time. Nice. I like it when it listens to me. Okay, so we already established that 23 centimeters is, in fact, the radius. So I'm going to put the measurement, 23 centimeters, that's the top part, and the word radius, that's the bottom part of my conversion factor. I did not want to make my conversion factor the reciprocal because right now radians in purple and radians in green are going to cancel, leaving me the only units that are left here are centimeters on the top and minutes on the bottom, and that is actually what the directions have asked me for, centimeters per minute right there. Okay, so I'm going to multiply straight across the top 48 pi times 23, and that will give me my final answer. For linear speed, would not make any sense to describe how fast your car is driving down the road as a linear speed to use pi, right? Your speedometer in your car doesn't have a pi on it, right? Oh, I'm going 20 pi miles per hour. Am I speeding? Who knows? All right, so we're not going to use the symbol pi in linear speed. We're going to multiply by the number pi. So 48 times pi times 23. I want that whole thing as like a decimal number. So 48 times I lives right here in the calculator. It's on my TI. You can see the little exponent button right there. I'm gonna have to hit Shift. Pi is right above that. So here's my blue second. There's pi, and then times the size of the radius. That was 23 equals. Wow, that's a big number. 3,468. 3468.3. 3468.38 centimeters per minute. That's a fast ladybug. It's also a terrible 8. Nobody can read that. Let's see if we can make this 8 more 8-ish. Okay. 8. That's better. Last question. Number 4. Number 4. The ladybug counts the little pits in the record. There's the little bumps in the like a vinyl record. It's got little bumps, and the needle picks up the little bumps. Those are actually the sounds as the needle bounces up and down on those little pits in the record. That's how record players work. So the ladybug does some counting on its own. It says there's 7 pits per centimeter on the record. So if Pepper extended a claw, turned himself into a gramophone, like Stitch, that'd be awesome, obviously. But what rate? What rate do the pits pass by Pepper's claw in pits per minute? Okay, this, well, I circled the wrong word. I'm trying to circle rate. Rate implies some kind of speed, right? And the directions here tell us oh man, we're looking for pits per minute. So in this context, pits is measuring the distance, right? We got all the on the record player. These little pits. They're spaced out, uniform rate of 7 pits per centimeter. Okay, we're using it as now we've kind of changed pits into a measurement of distance. So what I'm asked for, at what rate do the pits pass by Pepper's claw in pits per minute? That's also a linear speed. I just found a linear speed in number 3, and then question 4. I'm going to find a different set of units, still for linear speed. So I do not need a conversion factor out of my notes. I can take this previous linear speed of 3468.3 centimeters per minute and convert that from one type of linear speed to another type of linear speed by using the conversion factor that is described in the problem right here. It's 7 pits per centimeter. This is just straight unit conversion. 3468.3 centimeters per minute. And then I'm going to use my conversion factor, 7 pits per centimeter. If I set up my conversions in this way, I'll have centimeters in the numerator in red and centimeters in the denominator in blue. Centimeters will cancel. The only units that remain in this problem are pits on the top and minutes on the bottom, which is what I was asked for. So let's multiply. That previous number we had still should be in my calculator. Just multiply that by 7 times 7 is a very large number, 24,278.2. 24,278.2. 24,278.2 bits per minute. But wait, I think there's more. Oh my gosh. In the real life actual movie, when Stitch counted the record player, it was not going at the numbers that we just did. So let's try this. Let's try this. The real life movie, actually, Stitch counted the edge of the record to be moving at 5,000 centimeters per minute. And as Lilo measured the record She found the radius was 18 centimeters. What is the record's rotational speed in revolutions per minute? Oh my goodness. Okay, well, I know where I'm ending. It tells me I'm trying to end at rotational speed measured in revolutions per minute. We could call it rotations per minute, same thing for our purposes. Okay, so I'm trying to end at rotational speed. And here's what I'm given. I'm given 5,000 centimeters per minute. Well, I know a centimeter is a measurement of length or distance, and a minute is time, and so centimeters per minute. Let's look at our notes. Centimeters per minute seems to me like that's going to be a linear speed, distance and time, centimeters and minutes. So I have a linear speed. I was given that, and I am asked to convert that into rotational speed. So remember, our notes page, top rotational speed, bottom linear speed. Roll this into a circle. Sorry. Oh my gosh, I can't do this. Whew. Oh, it's creasing. Blam. So we can make linear speed and rotational speed touch. Bloop, bloop, top of the page, bottom of the page. And so the conversion factor, which is literally placed in between linear speed here in purple, and when we loop this, the green rotational speed is this conversion factor. To convert between linear speed and rotational speed, we need the word rotation or the word revolution or the word spin of the record player, and in quotation marks, the circumference. The quotation marks, that's the clue. I need to replace that word with an actual number for the circumference. We can calculate the circumference by doing 2 times pi times the radius. All right, let's take this 5,000 centimeters per minute that we just had identified earlier. That'll be our starting point. Make that 0 look like a 0. Okay, and then my conversion factor is going to be the size of the circumference and the word revolution. And in my notes, it had the word revolution on the top or rotation. I can change those. I'm going to write down revolution because the question asks me to give my answer in revolutions per minute. Revolutions and rotations basically interchangeable for our purposes. Okay, so my conversion factor, the denominator of this red conversion factor needs to be the actual circumference. So let's pretend this is my record player. Here's the center. Lilo measured the record to have a radius of 18 centimeters. So circumference 2 pi times 18, which if I do some mental math, that's going to be 36 pi centimeters. And maybe I don't want to leave pi in there, but I can take care of that later. You can multiply the 36 times the pi now or later. Okay, so the green centimeters in the numerator and the red centimeters in the denominator, those are going to cancel each other. The only units that remain at this point are revolutions on the top and minutes on the bottom. That is what the directions asked me for. So I've matched what the directions asked. I got the right conversion factors. I got them in there correctly. Everything is good. So I just need to multiply, or I guess in this case, I actually divide 5,000 divided by 36 pi. 5,000 divide by, and so if I just type in 36 pi, this is not going to work. If I type it in like this, my calculator is going to do 5,000 divided by 36, and that's it. Take that answer and then multiply it by pi, and that's not what I want. I want the 36 pi all to be in the denominator, so I need to have, just here, I'll show you. Here's what it's going to do the first time. That's wrong. And then let's type it in here again the second time. The right number of zeros, divide by, I'm going to use parentheses this time, 36 pi. So the lack of parentheses, super common cause of errors. You can see we totally get different answers there. 44.2 is what I do want, and that 436 is what a lot of times people get. And they'll be like, I typed it in right. I don't know what the problem is. Well, Yeah, calculators in parentheses. So 44.2. 44.2 revolutions per minute. Final answer. So thank you, Lilo and Stitch, for giving us an opportunity to do some important math